Okay, hello. Today we're going to solve this system of equations, and I do have a word problem associated with it, but we're just going to focus on this question, not how to get these equations. So, the normal way to do this would be isolating a variable, substituting, or maybe eliminating one of them, using Gaussian elimination if you're really fancy, but I'm going to do this a totally unnecessary way. So first, I'm going to write this system of equations in matrix form. So, we have a matrix 2, 1, 4, 1 multiplied by the vector xy equal to the vector with entries 100 and 36. And you can check to see that this is really true because just by matrix vector multiplication we get 2x times plus 4y equal to 100. And x plus y equal to 36. If you want, you can verify that yourself. Now, I'm going to call this this matrix A. So A is going to be equal to 2, 4, 1, 1. And what we're going to do is try to find an inverse matrix A to the minus 1. The reason for that is we'll be able to apply the inverse matrix on both sides of this equation, and we will isolate the vector xy and be left with another vector with nice values. So remember that if A is equal to a 2 by 2 matrix, A, B, C, D, the fact is the inverse matrix A to the minus 1 is actually just equal to 1 over the determinant of A, and then we have this matrix here. And in general, you're going to notice that this matrix is composed of the cofactors of each of the entries of A, but for a 2 by 2 vector, there's a very nice pattern. It ends up just being D minus B minus C A. Just like this. So, first we have to find the determinant of A, and then we can just plug in all of our values. So, the determinant of A is just AD minus BC. So, determinant of A is equal to, in this case, 2 minus 4, which is just equal to negative 2. Now, we can find our inverse matrix finally. And the thing to note here is that this obviously only applies when the determinant is not equal to 0, which is consistent with what we know about determinants and inverse matrices. So, A to the minus 1, the inverse matrix, is just 1 over minus 2 times D, which is just 1. And I'll put in A, which is 2. Then I'll negate the 4 and 1. Minus 4, minus 1. Just like that. Now, I'm going to, because 1 over minus 2 is just a scalar, I'll distribute it inside of this matrix to each entry. So, we're going to end up with minus 1/2, positive 2, positive 1/2, and then negative 1. And here's our inverse matrix. So we're going to come back to this equation, and we'll apply it to both sides. And so, we have minus 1/2 to 1/2 minus 1 applied to the original A, 2, 4, 1, 1, which is applied to xy. Just like that. And that is equal to applying the inverse matrix on the other side as well. It's minus 1/2, 1/2, 2, minus 1. And I'm running out of space here, so I'm just going to erase our result. I've written it twice already. 136. 136. And you'll notice this is the matrix, this is the inverse matrix. They cancel out, and we're left with just xy. This is exactly what we wanted. We have a vector xy equal to another vector. All we need to do is multiply this vector by this matrix to get our final answer. So, this means that xy is just equal to 100 times minus 1/2 is minus 50. 36 times 2 is 72, positive. And next, 100 times 1/2 is positive 50. 36 times minus 1 is minus 36. And our final answer is just going to be 22/14. So this means that x is equal to 22 and y equals 14. And there we have it. We did it in an unnecessarily complicated way using linear algebra, even though we could have just used elimination.